Hello everyone, thank you very much for your interest in this work. This poster is titled Characterization of Structural Chains in Ramon's Starch Cerogels and Cryogels, and is part of a project to implement these porous materials obtained from starch as scaffolds in the field of tissue engineering. Aerogels are porous materials, usually obtained using supercritical drying to separate the liquid from the solid phase of hydrogel, leaving the three-dimensional structure as intact as is possible. In this part of the project, we focus on the process of obtaining porous aerogel type materials obtained by two different drying methods, vacuum drying and freeze drying, and we will produce them using Ramon seed starch. Starch is a polysaccharide, one of the most abundant on the planet, which exhibits biodegradability and biocompatibility. It has been studied in recent decades in the production of aerogels as a substitute for the most common silica aerogels. In addition to the properties already mentioned, starch provides these materials with other properties such as being more rigid, opaque, and generally more resistant to compression, as well as they are hydrophilic. The starch we use is isolated from the seed of a tree called ramon, an endemic tree in Mexico and very common in warm areas such as Quintana Roo and Yucatan. It is often consumed by some communities and is also marketed as flour. However, most of the seeds are discarded, so using the starch from this seed allows us to give it a functional value. As part of the methodology for producing these materials, a starch dispersion is gelatinized at a temperature of 90 degrees Celsius under magnetic stirring for 1 hour, and then sterilized in an autoclave to completely rupture the starch granules. The samples are refrigerated, allowing the starch to retrograde. And then we use the two drying methods mentioned before. This figure shows a comparison of the gels obtained. Additionally, prior to the comparison between drying methods, we study the effect of the different retrogradation times and the starch concentrations on the production of cerogels, as we can see in this table. As a result of this preliminary study, we were able to see that as the retrogradation time increased, the mesoporosity of these materials was lost, and they present areas of retrograded starch without pores. This has been related to the fact that increasing the retrogradation time created fibrillar structures that collapse under high capillary tension. And as we can see, after 3 days of retrogradation, the sepals present these homogeneous porous areas that appear to be interconnected. Compared to the native granules in cryos, we can see how after gelatinization, the granular structure is lost and the gel structure is generated. The cryols present large structures formed by ice crystals. In the FEIR spectra, we can observe signals related to the structural change in the starch. Principles and these signals are present in 1096 and 996, which refer or are related to changes in the amorphous component of the starches. We can see how the radio of these signals increases with the increasing concentration, which can be attributed to a reduction in the crystalline component. The same can be seen when comparing cryols and cerogels, where it is notable that the cryols after gelatinization exhibit a greater degree of reorganization. Regarding the TGA thermograms, we observe an increase in their degradation temperature and a reduction in residues, which is partly related to the reorganization of the starch chains, but can also be attributed to the porous structure of the material. Finally, regarding some of the functional properties of these materials, we find pore size, density, shrink rate, and percentage of porosity. These figures present a comparison between cryols and cerogels, where their differences are notable. Cryols have macropores of up to 60 micrometers, a high percentage of porosity, and a low density. Cerogels, on the other hand, have a pore size below 100 nanometers, a low percentage of porosity, and a high density. As conclusion, porous materials were obtained from Ramon seed starch. Vacuum drying results in high shrinkage and reduced porosity. Freeze drying allows obtaining materials with macropores and low density. and both drying techniques generated a structure change in the starch chains and increased thermal resistance. As acknowledgements, the authors are grateful for the support of the institutions and researchers involved and for the scholarships granted by CICITI for this work. Especially thanks for our colleague Montserrat Santiago Hernandez for her support in the experimental work. This is the reference using in the poster, and thank you for watching. I hope see you in the Congress. Thank you.